Hey guys, welcome back to another video. This is topic 2.8, inverse functions. An inverse relation will undo a given relation. Every inverse relation can be found by switching each x and y value. In some situations, this process is intuitive, but other times this may not be as obvious. In these cases, it is important that we understand the concept of inverse relations, as they will help us tackle a variety of problems. Let's look at this numerically, graphically, and analytically. The first type that we will do is off of a table. Example 1 says, find the inverse relation of the given table. So if we just discussed that to find the inverse, all you're going to do is switch the x and the y values. That means that we're going to put these here and these over here. So all you're going to do is switch them. So for the x values of the inverse, we're going to write -1, 2, 0, and 2. And for the y values, it'll be 1, 3, 4, and 6. So all you do is take the original x values and they'll be the y values of the inverse. And the original y values will be the x values of the inverse. They do not switch signs. Okay, so don't change the signs. Don't make a negative into a positive and vice versa. That's not what you're doing. All you're doing is switching the x and the y values. Okay, now if you remember what a function is when every x value maps to only one y value. So the original table, if you look at the x values, we have 4 different x values. So none of the x values repeat. So we can say that the original table is a function because each x value has exactly one y value. Okay? But if you look at the inverse table, notice that this 2 here is repeated and they have different y values. So that means that the inverse is not a function because the x value 2 has 2 different y values, which are 3 and 6. Okay. Now, that was numerically. Now let's try graphically. Example 2 says, sketch the inverse relation of the given graph. So here are the steps to sketch an inverse graph that has linear pieces. So that's going to be when you have several line segments put together. We're going to do some that are a little bit more complex where it's like a curve. So those are going to have different steps. But if everything you have is linear, these are the steps you're going to take. The first thing you're going to do is list the key points in a table. And the key points are the endpoints of each line segment. Then you're going to create a new table for the inverse by switching the x and the y values. And then you can plot the new points for the inverse and sketch the inverse graph. Okay, so I'm going to put the tables over here. So I'm going to put the original table, and then we'll do the inverse table. And for both, I'm going to have x and y values. Okay, so to fill in my original table, I just need to get the endpoints from each line segment. So these are endpoints, these are endpoints, and these are endpoints. So notice that my line starts and ends at the bubbles here, and then this one starts and ends there, and that one. So you don't want to pick points that are like here, because, I mean, you can, but it's going to be a waste of time, because if you have the endpoints and you connect a straight line, you're going to get all the middle points anyway. So you just need the endpoints, okay? So from the original table, I have -2 and -1. My next coordinate point is -1, 2. Next, we have 2 and +1. And finally, we have 4, 3. Okay, now for the inverse table, all I need to do is switch the x and the y values. So I'm going to have -1, -2, 2, -1. I'm going to have 1 and 2, and 3, 4. And now these points, I can go ahead and graph them. So -1, -2, 2, -1. Okay, I have my first 2 points. I can go ahead and connect those. Now I'm going to move on to 1, +2. I have 2 more points that I can connect. So I'm going to bring these together. And then the last one is 3, 4, which I can then connect here. Okay, so there is the graph. Example 2b says, is the original relation a function? Now, graphically, you can use the vertical line test to determine if a graph is a function. So if you look at the original relation, which is the solid black one, and if I were to draw vertical lines throughout, now the vertical line test says it can only touch one time. So here, so far it passes the vertical line test. Here it passes the vertical line test. Same thing here, it passes the vertical line test, passes the vertical line test. Remember that I'm only looking at the original one that's in solid black. So anywhere I draw a vertical line, the original relation does pass the vertical line test. Okay, so that means the original relation is a function. So I'm going to say the original relation is a function. Now the only thing is you cannot say because it passes the vertical line test. So on the AP exam, if you put that as your reasoning, it will be counted wrong automatically. So if you're gonna prove whether something is a function or not, you need to say because each x value has exactly one y value. Okay, so you can use the vertical line test as a strategy, but you cannot put it in your answer that it's a function because it passes the vertical line test. Okay, you have to say because each x value has exactly one y value. Now, the follow-up question says, is the inverse relation a function? So that's the solid pink. So if I draw a vertical line test, it passes here, it passes here, but notice what happens when I get to 1. When I get to x equals 1, I already have a point here, and now I have another one there. So it fails as soon as I get to x equals 1. What happens if I go to 1.5? It touches once, twice, 3 times. And when I get to x equals 2, it's touching here and there. Okay, so notice that everything between x equals 1 and x equals 2, it fails the vertical line test. But if you're only looking at this line segment on the front and the back end, this part passes the vertical line test, and so does this part. But again, everything from 1 to 2 fails the vertical line test because it touches 2 or 3 times, meaning that those x values have 2 or more y values. Okay, so we're going to say the inverse relation is not a function because each x value between 1 and 2 has 2 or 3 different y values. Okay. All right. So the graphs of inverses are reflections over the line y equals x. Okay, now y equals x is a linear equation. Since it does not have a coefficient, that means there is an imaginary 1 in the front. So that means that the slope is 1. Okay, that means when you do your rise over run, you're going to be going up 1 over 1, up 1 over 1. And the y-intercept, since there's nothing there, that means the y-intercept has to be 0. Okay, so just remember the equation was mx plus b, right? Since this is not there, the only thing the y-intercept could be is plus 0, because it would still be equal to x. Okay, and then again, the slope, there is an imaginary 1 that is a coefficient of x. So when you draw your y equals x line, I recommend that you start at 0 and you're going to draw a dashed line through 0 because that's your y-intercept. And you're going to be going from 0 up 1 over 1, up 1 over 1, up 1 over 1, etc. So you're going to want to make sure that you start at 0 and then you're going to draw a dashed line. And I'm drawing my line through the little grid, like through the little squares, to try to make it as straight as I can. And then I will be labeling this line y equals x. Okay, now what that line does is that is equally spaced in the middle from the original relation to the inverse relation. So you can see these are equally a distance from y equals x. So your inverse and your original are the same distance from y equals x because they are reflected across y equals x. So if I were to fold it diagonally, they would overlap. Okay, let's go to the next page. Okay, so we've done numerically, we did graphically. Now we're going to do analytically, which are equations. So here are the steps to find an inverse equation. The first step is to switch the x and the y values, and you want to solve for y, meaning that you want to get y by itself. If the original equation was in f of x form, write the inverse as the inverse of f of x. And then just a reminder that just a reminder that f of x is the same thing as y. So example 3 says find the inverse for f of x equals 3x minus 7. Okay, so just remember that f of x is the same thing as y. So if you want to, you can rewrite this as y equals 3x minus 7. But the first step is to switch your x and y values. So I'm first going to write x equals 3y minus 7. And I want to solve for y, so I need to get y by itself. So I'm going to add 7 on both sides. I get x plus 7 is 3y. Then I'm going to divide both sides by 3. And then I'm going to have x plus 7 over 3 equals y. So now that I have y by itself, I can proceed to step 3, which is to write the inverse equation in the correct notation. So the inverse function of f of x is written in this notation. It is not read as f to the power of negative 1, though it's just read as the inverse of f of x, okay? So the inverse of f of x equals x plus 7 divided by 3. Okay, so it's pretty easy when you just have a linear equation that's given to you. Now let's try finding the inverse of rational functions, okay? That means if you remember from the second half of Unit 1, where you have a polynomial with x in the numerator and a polynomial with x also in the denominator. So here are the steps. Step 1 is still going to be to switch your x and y values. Step 2, you're going to multiply and distribute both sides by the denominator to eliminate the fraction. You're going to move all the terms that have the variable y to the left side and all the terms that don't have y to the right side. Then you're going to factor out any y factor out the y from the terms on the left side of the equation, and then divide both sides by the terms remaining on the left side after y was factored out, and then rewrite the equation with proper inverse notation. So again, I'm going to start by putting y equals here, and then we're going to be switching the x and the y values. So I'm going to write x equals y minus 2 divided by y plus 3. The first thing you want to do is multiply the denominator on both sides so that you can get rid of the fraction. So then these would cancel out. In this same step, you're going to distribute that x into that binomial. So we have xy plus 3x is equal to y minus 2. The next step is to move all the terms that have y to the left. So if you look at the right side here, I have a y that I want to move to the left, so I'm going to subtract it on both sides. So now we have xy minus y plus 3x equals negative 2. Now, on the left side, we said we should only have y. I have y, but this term does not have a y, so I'm going to want to move that term to the right side. So now we have xy minus y is equal to negative 3x minus 2, okay? So notice that here's the equal, so everything on the left, this term has a y, that term has a y, and then nothing here has the variable y. So now that we've done that part, we can move on to step 4, which is to factor out y from the terms on the left. So if I take y out, and factoring out the y is the same as dividing both of these by y, okay? So these cancel out, they equal 1, these cancel out, they equal 1. So I'm left with x times 1, which is just x, and then the other one we just have 1, okay? Now notice that on this side the x is negative. If that happens, just factor out a negative as well. You want to make sure that your x variable is positive, and then if you factor out the negative, that's the same thing as dividing both of these by a negative 1. So if you do that, these will cancel out, right? So you would just end up with positive 3x and then plus 2. All right, step 5 is divide both sides by the terms remaining on the left side. So on the left side, I have left x minus 1. Okay, so then these cancel out, and we have y equals negative 3x. You don't have to keep the parentheses anymore. 3x plus 2 over x minus 1. And then step 6 is to rewrite the equation using the proper notation. So what we can do is I'm just going to erase this y and write it in inverse notation. So the inverse of f of x is equal to negative 3x plus 2 divided by x minus 1. Okay? All right, let's do another example. So first thing, change g of x to y, and then I'm going to switch my x and y values. So we have x equals 2y plus 1 divided by y minus 3. I'm going to multiply both sides by the denominator so that I can get rid of the fraction, and then I'm going to distribute the x into the binomial, and I have xy minus 3x equals 2y plus 1. Okay, I want to get all the terms that have y to the left side, so I'm going to do minus 2y. Now on the same step, so if you prefer, you can do this in 2 steps. You can move the y's to the left and then everything else move it to the right. Alternatively, you can also do it all in one step. So I'm going to show you that. If you don't feel comfortable with it, you can do it in 2 steps, okay? But since I already know what I'm doing, I can do this in 1 step. So I know that I'm also going to want to move the 3x to the right. So I'm going to move at the same time something from the left to the right and something from the right to the left. Okay, so these two cancel out. So to recap, I moved this term to the right and I moved this term to the left. So I'm moving something from one side to the opposite side, but on both sides. So I'm doing 2 things at the same time. So again, if you do not feel comfortable with that, you are not forced to do it that way. You can do it in 2 steps, 2 separate steps, okay? All right, after you have all of your y variables on the left and no y variables on the right, you move on to step 4, which is to factor out the y. If you divide both of these by y, these would cancel out and you're just left with x minus 2. Notice that on the right side, the x is positive this time, so we do not have to do the extra step of factoring out a negative. So you only factor the negative if your x is negative. If it's positive, you can skip that step. So now we have y equals 3x plus 1 divided by x minus 2. And then the last step is rewrite using the proper notation. So I'm going to erase y and I'm going to write the inverse of g of x. Okay, so there you have it. You have 2 examples there. As long as you follow the steps, you should be good. Okay, so again, if you prefer to do it in 2 steps versus 1 step, that is completely your choice. So please don't feel forced to do it the shorter way if you do not feel comfortable with that. Okay, more on graphing inverses. We know that to find an inverse, we simply switch the x and the y values. Graphically, this means that a function and its inverse will be reflections over the line y equals x. If a graph is not made up of simply line segments, sketching the inverse can be challenging. To do this, we use the fact that a function and its inverse are reflections over the line y equals x to help us sketch the inverse graph. So here are the steps to sketch non-linear pieces. First, you're going to sketch the line y equals x on the graph. Mark any points from the original graph that are already on the line y equals x. These points will stay the same. Select a few additional points on the original graph and find their inverse points. You can find the inverse points by switching the x and y values, or graphically reflecting each point over the line y equals x by drawing a line that is perpendicular from the point to the line y equals x and extending it an equal distance on the other side of the line. Sketch the inverse graph by connecting the new points in a similar pattern to the original function. Okay, so here is example 5. Sketch the inverse of the functions below. So I'm going to start off. Step 1 is sketch the line y equals x. So remember, you're going to start with the y-intercept of 0, and you want to go up 1 over 1. And I'm going through the corners of the little grid to keep my line straight. Okay, and I'm going to label my line y equals x. Step 2 is to mark any points that are already on the line. So I have this point here and that point that are already on the y equals x line. The reason that they stay is because this point at 4, 4 and this point at 1, 1, if you switch them around, if you switch the x and the y values, you end up with the same point. So that's why those 2 points are both on the original graph and on the inverse graph. Okay, so now what I want to do is grab some other points. So I'm just going to go through and make some marks here. So we have 0, 4, which is this point here. So if I take the inverse of that, I would end up with 4, 0, which would be down here. So this one would be 4, 0. Okay, I can keep going. I see I have another point here at 2, 0. If I take the inverse, I would be at 0, 2. Let's see if I find another point. I have this one at 3, 1. So if I take the inverse, we would be at 1, 3. Okay, and I think that's about it. We can get more, we can approximate decimals, but we do have enough points that I think we can make a pretty good sketch. So I'm gonna grab these points and connect them as best as, yeah, it's kind of hard You want to avoid that mistake that I'm making, which is making my vertex pointy because it should be more round. Okay, so you grab this parabola, and then when you take the inverse, it turns on its side like this. Okay, so that is the inverse graph. Let's try another one. So again, the first step is to sketch y equals x. So I'm drawing first a little line through the origin to represent my y-intercept at 0. And then I'm going to keep going up diagonally, going through the little grid intersection right there in between the little box. And I'm going to go down the other side as well. Okay? And I'm going to label that y equals x. Now, step 2 is mark any points that are already overlapping on y equals x, which would be this one, and that one. Okay, now let's find some points. Now notice that on this one, we did grab the minimum value here. So whenever you have any like minimums and maximums, you want to make sure to get those points so that you know where they're supposed to be. So for example, this point here approximately might be like negative 1.2 and positive 2.1. That's just an approximation. It doesn't have to be perfect. But when we sketch it, the inverse will be at 2.1 and negative 1.2, maybe somewhere like right here. So positive 2.1 and negative 1.2. Okay, and then here's the other minimum, which would be like a positive 0.5 and negative 0.5. So when I take the inverse, I would be instead at negative 0.5, positive 0.5, perhaps somewhere right here. Okay, now let's see if there's other points. I see this one that is at negative 2, 0. If I take the inverse, that would be at 0, negative 2. And let's see what else we have. Okay, I don't see anything that's perfectly aligned. So let's see if we can make the sketch with just these points. So this should go this way. And then back out the other way like this. Okay, so we went from going up to instead going sideways. Okay, so it looks more like the letter S. The inverse looks like the letter S. Okay, so what do inverse functions do? If you plug a number into a function, it generally will output a new or a different number. For example, if we plug in x equals 2 into the function f of x equals 3x minus 1, we would get f of 2 is 3 times 2 minus 1, where you get 5. Okay, so you're plugging in this x value into every x. So you get 5. So if I were to write this as a coordinate point, the original coordinate point, right? I plugged in 2 and my output was 5. Now, if we were to plug that answer into the inverse function, the answer should be what you started with, which was 2. Because if you take the inverse of this point, that point would be 5, 2. Okay? So if I ask you to plug in 2 and you get 5, and then you plug that answer into the inverse, that answer will be 2, which is what you started with. Okay? This is because an inverse function essentially will undo a function. So we plug x into a function, right? So if you plug x into a function, you're going to get y. And if you plug that y into a function, you're going to get x, because remember that the inverse is just switching the x and the y values. So you're going to end up with x, which is what you started with. So when you plug the output into the inverse, we should end up with x again. Okay, let's go to the next page. So inverse functions. Two functions, f of x and g of x, are inverses if and only if f of g of x equals x and g of f of x equals x. To show that two functions are inverses, we must show that the inverse of f of x and f of the inverse of f of x both equal x. Okay, so now we're going to be combining composition, which was our lesson from 2.7. So they both have to equal x. Okay, so example 6, let f of x and g of x be the functions below. Determine if f of x and g of x are inverses. So step 1, find f of g of x. The first thing you need to do is figure out what is on the inside of the composition. I see the inside has g of x, which is 1/2 x plus 3 over 2. That answer, I'm going to plug it into f of x. So I'm going to do f of 1/2 x plus 3 over 2. If I plug that into f, which is 2x minus 3, I would have 2 times 1/2 x plus 3 over 2. And then on the outside, I still have minus 3. So notice that, again, these are the same exact equation, just that this was f of x equals 2x minus 3, right? The only thing is that our new x is the entire equation of g. So this is what's going in the parentheses, 1/2 x plus 3 over 2, okay? Now at this step, you would distribute the 2 into here. Now I see that I'm distributing into fractions. To multiply fractions easier, what you could do is change the whole number to be divided by 1. And I'm going to break it up a little further than I normally would. If you know how to multiply fractions, you do not need to do it in this much detail. This is just to break it down for kids who really struggle with multiplying fractions without a calculator. So the first thing I need to do is multiply 2 over 1 times 1/2. So I'm going to break it up, 2 over 1 times 1/2 x. Then I'm multiplying 2 over 1 by 3 over 2. And then minus 3, okay? Now to multiply fractions, you multiply straight across. So before you multiply straight across, you want to analyze your fractions, because if anything cancels out on the top and the bottom, for example, these 2's cancel out and this 1 over 1, they don't like disappear, they equal 1. So this equals 1, this equals 1, and 1 times 1 is still 1, okay? Now on this side, we have 2 divided by 2, so this side also equals 1. So here we have 1 times 1, which is 1, and 1 times x is still just x. And on this side we have 1 times 3, which is just 3, and then we still have the minus 3 that was on the back. X plus 3 minus 3, the plus 3 and the minus 3 equal 0, so this equals 0. So finally, we are just left with x, okay? Now let's see if the opposite order is still x. Let's try g of f of x, starting with the inside, which is f of x. F of x is 2x minus 3. I'm going to put that into the equation for g. So I'm going to be solving for g of 2x minus 3, which would be 1/2 2x minus 3 plus 3 over 2. Okay, so just to show you, these two are identical. The only difference is that this 2x minus 3 just used to be x. G of x is 1/2 x plus 3 over 2. Okay, now just like the other one, we need to distribute this 1/2 in here. But when you multiply fractions, if it helps you to put things over 1, I would recommend that. So I'm going to put the 2 over 1 and the 3 over 1. And then I'm going to break it up on here. So we have 1/2 times 2 over 1x plus 1/2 times negative 3 over 1. And then I still have a plus 3 over 2 on the back. Okay, so again, just to recap, this is this part here. I'm just breaking it up, multiplying the 1/2 into the binomial. Okay, so again, you want to analyze what you have. So these 2's cancel out, the 1's cancel out. They both equal 1. They don't disappear, okay? And then here, these 1's also equal 1. 1 divided by 1 is still 1, okay? So on this side, if all I'm left with is 1 times 1, which is just 1, and 1 times x is just x, I can put equals x. And then here you just multiply straight across, or you can just see what you're left with, which is negative 3 over 2. And then we still have the plus 3 over 2. And then these equal 0. They cancel out and they equal 0. And so your final answer is x. Okay? So we have determined that f of x and g of x are inverses of each other, because when you compose them and do f of g of x and g of f of x, both of them equal x. Okay, so this is how you would prove whether two functions are inverses of each other. Here is a note. Sometimes we must use a restricted domain to ensure that two fractions are inverses. Example 7 says show that h of x and k of x below are inverses where x is greater than or equal to 10. Okay, so I'm going to graph this for you just so I can show you why restricting the domain is important. Excuse me. We have x squared plus 10 . Okay, there it is, x squared plus 10. And now I'm going to type the other one, which was the square root of x minus 10. Okay, now notice that they're similar, but they're not the same. So the reason why is that if you remember, I told you a while ago, anytime you take the square root of a number, so for example, if I say x squared equals 4, and you want to take the square root so that you can solve for x, because you know that the square root and the square cancel out. I told you that anytime you take the square root of a number, you always need to put plus or minus and then whatever the square root number is. Okay? The reason why is because I could have 2 times positive 2, or I could have negative 2 times negative 2. And both of those equal a positive 4, which is what we had started with over here. We had a positive 4. So that's why you always need to account for the option that the square root could be positive or negative. Okay, so what happens is the square root function is always going to be half of the parabola. If you want to see the whole parabola flipped on its side, you have to add an additional equation, which would be the negative square root of whatever you have going on, which we had was x minus 10. And I do have a negative in the front, and you can see that now we have the whole parabola flipped on its side. And the red function, the f2 and the f3 put together, make that parabola flipped on its side. The reason that they have to restrict the domain is because, excuse me, the reason you have to restrict the domain is because if you were to put both the positive and the negative square root, it would fail the vertical line test. Okay, so if you have it like this, notice that you would fail the vertical line test because you would touch 2 times. So a lot of x values, all of the x values except the vertex, will have 2x. One x value will have 2 y values, so it would not be a function. So they restrict the domain to just 1/2. So you either get the positive square root of x or somewhere else you would get just a negative square root of x. So that when you do the vertical line test, it passes the vertical line test, whether you're looking at the positive side or the negative side. But if you put them together, it'll always fail the vertical line test. So that's why the domain restriction is important, okay? Because otherwise your inverse will not be a function. Okay, so we're going to show that h of x and k of x are inverses. So I need to do composition, and I'm going to compose them into each other. So the first thing I'll do is h of k of x, and I'll also try it in the other order, which is k of h of x. Now I'm going to replace k of x with the actual equation, which is the square root of x minus 10. That will be my new x value for h of x. So I'm going to have the square root of x minus 10 squared plus 10. I know that the square root and the square cancel out. So here I am left with x minus 10 plus 10. I also know that negative 10 and positive 10 equal 0. So I would just be left with x. Okay, let's try the other order. So we have k, and then inside the equation of h of x is x squared plus 10. Into k, I will put the square root of x squared plus 10, and then there is also an additional minus 10 in there. So just to show you, these two are the same, just that this x is now x squared plus 10. But it used to be just k of x equals the square root of x minus 10. Okay, now in here, I can cancel out the 10 and the negative 10. So I would be left with the square root of x squared. And we know the square root and the square cancel. So I would just be left with x. So I have shown that h of x and k of x are inverses only where x is greater than or equal to 10. Okay, so without the domain restriction, it wouldn't work. Remember that the square root has to have a domain restriction. Example 8, show that n of x and p of x below are inverses where x does not equal 0 and x does not equal 4. Okay, the reason that they put these domain restrictions is because we know that the denominator can never equal 0. So if I set this equal to 0, I get x equals 4, and if I set this one equal to 0, we get x equals 0, and we cannot have zeros in the denominator. So that's why these domain restrictions are important. We need to skip over the values that are going to give us an undefined output. Okay, so now we're going to do composition in both directions. It doesn't matter which one you do first, because you need to do both of them, and both of them need to give you x. So as long as you do them both and you get x, it doesn't matter which one you do first. Okay, so we have n of 6 over x plus 4. So I'm replacing the equation of p in the parentheses, and I'm going to put this into the x value of n. So we have 6 over x plus 4, and then I still have a minus 4. I can simplify in the bottom, the 4 and the minus 4 cancel out, they equal 0. So I would be left with 6 over 6 divided by x. To divide fractions, you're going to do keep, change, flip, which means that you're going to keep the numerator, you're going to change the sign to multiplication, and then you're going to flip the fraction in the bottom. And then you can see that these 6's cancel out. If you want to put this 6 over 1, you can. But either way, you're just left with x. Okay, so that one checks out. Now on this one, the second one, I'm going to write the equation of n of x inside the parentheses. Okay, so we have n of x here. N of x is 6 over x minus 4. And I'm going to put this one into the x of p. So we're going to have 6 divided by 6 over x minus 4. And then outside we're going to have plus 4. Okay, so we have another fraction that we need to divide. So we're going to do keep, change, flip again. So I'm going to keep the numerator, change the sign, and then flip the bottom. And again, if you want to put this 6 divided by 1, you can. And then we still have a plus 4 on the back. Now, according to PEMDAS, we have to do multiplication before we do addition. So I first need to multiply these together before I add the 4. Okay? Now notice that these 6's here are going to cancel out. So I'm just left with x minus 4 plus 4, where minus 4 plus 4 equals 0. So we are just left with x. Okay, so that's how we can show that these two are inverses. When you compose them within each other, both of the answers end up being x. Okay, on the next page, we have inverse functions. If f and g are inverse functions, then g of x equals the inverse of f of x. If xy is a point on the graph of f of x, then yx is a point on the graph of g of x. With inverse functions, all of the x and y values are switched, so the graphical behaviors in terms of x and y will also be switched. For example, the domain of f is the range of the inverse of f of x. A continuous function will only have an inverse function if it is strictly increasing or strictly decreasing. If a function changes from increasing to decreasing or vice versa, it will not pass the horizontal line test, and its inverse relation will not pass the vertical line test as a result. Alright, let's try example 1. Let f be a continuous function with selected values in the table below. Let g be the inverse of f, such that g of x is the inverse of f of x. Find the following values if possible. So the first thing I want to do is create my table for the inverse. Now, the inverse, they told me the inverse of f of x, they told me is the same thing in this scenario as g of x, because that's what they told me here. They said the inverse of f of x is equal to g of x. So I can put those on the same table because they're representing the same function, okay? And now all I'm going to do is flip my x. I'm going to switch my x and y values. So we have 6 and negative 3. And then I have 3, negative 2. And then we have 1, 0. Negative 1, 1. We have negative 3, 4. And then finally we have negative 7 and 6. Okay. So let's start with letter A, f of 0. This is exactly like what we did in 2.7. So you first do the inside. The table for f is here. We're evaluating when x equals 0, which is here, and that value is 1. So f of 0 is 1. I now need to do it again because it was f of f. So I'm going to put f of 1. And I'm going to go to the table of f, and when x equals 1, y equals negative 1. So this whole thing is equal to negative 1. Okay, let's try g of negative 3. G of negative 3 would be on this table, and when I go to the x value negative 3, I see that the y value is positive 4. So g of negative 3 is positive 4. G of 6, I'm going to go to the table for g, and I see the x value of 6 has a y value of negative 3. G of negative 1. I first need to find g of negative 1. So I go to the graph of g, the table for g, and find x equals negative 1, and the y value is positive 1. Now I'm going to do g of positive 1, and on here, when x is 1, y is 0. So that means that g of negative 1 is 0. Next, we have the inverse of f composed with f of negative 2, which I can rewrite as in this notation. It's the same thing, but if you're more comfortable with this notation, you can rewrite it that way. And then I also know that the inverse of f is also g. So we're really just doing g of f of negative 2, where I first need to find f of negative 2. So I go to the table for f of x, and when x is negative 2, the y value is 3. So f of negative 2 is 3. Now I'm going to find g of 3. So I'm going to go to the table, and when x equals 3, y is negative 2. So the inverse of f composed with f of negative 2 is equal to negative 2. Next, we have the inverse of f of negative 3, which is again the same thing as g of negative 3. And if you go to the table for g, when x is negative 3, the y value is positive 4. So the inverse of f of negative 3 is positive 4. Okay, so those are not too bad. Those are just, reusing skills that we learned in 2.7. Example 2 here says the function k is defined over the interval negative 4 to 11 as shown above. Let the inverse of k represent the inverse of k. And then it asks what is the minimum value of k of x and what is the minimum value of the inverse of k of x. Okay, what I would like to do first is find the domain in the range of k of x. Okay, now in the question they did tell me what the domain is for k of x. They said it was negative 4 to 11. I'm just going to write it in interval notation instead of inequality notation. But you can see that the domain, the smallest x was negative 4 and the largest x was positive 11. So that's the range. So even if it's not given to you, you can see it on the graph. For example, the range, the smallest y value is negative 3 and the largest y value is positive 6. So my range will be negative 3 to 6. Okay. Now earlier we highlighted that all of the graphical behaviors also switch, so the domain will be the range of the inverse. So to find the domain and range of the inverse of k of x, all I need to do is switch the original domain and range. So the new domain will be the old range, which was negative 3 to 6, and the range will be the old domain, which was negative 4 to 11. Okay. Now I can start graphing. The first thing I want to do is sketch the y equals x line. So I'm going to start by making a dash through 0 and then going up 1 over 1, up 1 over 1, like so. And when I get to the top, I come back and do the bottom part. Okay, and I'm going to label this line y equals x. Now since these are line segments, I can just make a table. Or you can also just find the point. So here we have negative 4, negative 3, which will become negative 3, negative 4 down here. And remember, I'm only using the endpoints because these are line segments. So 4, negative 1 will become negative 1, positive 4. Then we have here 6, 4, which will become 4, 6. And finally, we have 11, 6, which will become 6, 11. So that one kind of goes off the grid, but it'll be somewhere up there. Okay, now we can connect these points. This will go up like this. This one connects here, and then this one goes all the way up, where again this point was the 6, 11. Okay. All right, so there we have the graph. They want to know what is the minimum value of k of x. K of x is the black solid. The minimum value is just the minimum value is the smallest y value. Okay, so the smallest y value for the original k of x, the smallest y value is here at -3. Okay, so we're going to say the minimum value of k of x is -3. And then it asks what is the minimum value of the inverse of k. The inverse is the pink one. Notice that the smallest y value is down here at -4. So the minimum value of the inverse of k of x is -4. Okay. Another way you could have done it without having to even look at the graph is that if I'm asking you what is the smallest y value, the smallest y value would be the first value in the range, which is your smallest possible y value. So for k of x, the minimum was -3, which is what we had. And for the inverse, the smallest y value was -4, which is what we had. So you can use the domain and range to figure out your minimums and maximums, or if you want to go through the process of graphing the inverse and looking at it visually, you can do that too. So either or you can use both to double check your work, okay? The next thing we're going to do is find the inverse of k of 6, okay? So remember that these are x values, so I'm going to go to x equals 6 and x equals 4. And this is for the inverse of k. So I'm gonna try to match to the pink line. Okay. So when x equals 6 and I go up to the pink line, I have a point at 11. So the inverse of k of 6 is 11. Next, we're gonna do the inverse of k of 4. So I'm gonna go to where x equals 4, and I'm gonna go up to the pink, and at x equals 4, that y value is 6. Okay, let's do another example. So example 3 says that the function f is defined over the interval -2 to 8 as shown above. Let the inverse of f represent the inverse of f. What is the maximum value of the inverse of f of x? Okay, so the first thing we can do is find the domain and range of f of x, and then we can flip them to find the domain and range of the inverse of f of x. So the domain was given to us, it was -2 to 8. And then the range, you can see it visually, the smallest y value was -3 and the largest was +7. So the range is -3 to +7. So for the inverse of f of x, your domain and range will be the ones we just found, but you're going to switch them. So the range becomes the domain, and the domain becomes the range, like so. Okay? Excuse me. I had to sneeze. Okay. So what is the maximum value of the inverse of f of x? Let's go ahead and sketch this. So again, starting at the y-intercept 0 for the line y equals x, and then making sure your line has a slope of 1, and then you go through and make your little dashed line. I go all the way up, and then I come back down and finish the other side. and then this is y equals x, okay? So I'm going to grab some coordinate points. Here I have -2 and 7. So when I flip them, I would get 7, -2. Next, I have this one, which is at 2, 3. So when I flip it, it will be at 3 and 2. Next, I have this one down here at 4, -1. So when I switch them, it'll be -1, +4. And then the last one is at 8, -3. So when I switch them, I would have -3 and then +8. Somewhere up here perhaps. And then I can connect all these together. And it should look something like this. So what is the maximum value of the inverse, which is the one in pink? The maximum value here was 7. Wait. Oh, no, it wasn't. That was the other one. This point here came from, it was -3 and 8 because it came from this one that we switched to over here. So the highest y value was 8. Okay, so the maximum value of the inverse of f of x is 8. And you only include the y value. And then don't forget that you could have also looked at the range. So the inverse of f of x is here, and the biggest range number was 8. So that was the maximum. So you could look at it graphically, or you can look at it from the range. The next part says find the inverse of f of 3 and find the inverse of f of 1. Okay, so I'm going to go to where x equals 3, and I'm going to find the pink line, and I see that y value is 2. And then I'm going to go to where x equals 1. I'm going to find the pink line, which is my inverse, and the y value there is 3. Okay, and then finally, what is the domain of the inverse? We already found that. We found that the domain is the old range, which was -3 to 7. So we'll say the domain of the inverse of f of x is -3 to 7. Okay, one more example, example 4. The function g is defined over the interval from -3 to 10 as shown above. Let the inverse of g represent the inverse of g. Values of the increasing function h are given in the table above for selected values of x. Find the following if possible. Okay, so this one, notice that there's two different things going on because we have the graph of g and the table for h. So we're going to have to find the inverse for both. Okay, because I can already see at first glance we have the inverse of g here, the inverse of h, so we are going to have to do that. So to find the graph inverse of g, I first am going to sketch my y equals x line, starting at the origin and making my diagonal line. And then I'm going to label it y equals x. Now, since these are line segments, all I need to do is find the endpoints. So we have -3, 6, which will become 6, -3. Next, I have 3, 4, which will become 4, 3. Next, we have this one, which is 6, 1, That one will, when I switch them, will be 1, 6. And finally, we have 10 and negative 1. And when I switch them, I get negative 1 and 10, which would be somewhere like all the way up here. Okay, this one is negative 1, 10. And then I can connect them. Okay, so that's the inverse of G. Now we can find the inverse of H. So I need to make a new table for the inverse of H of X. And all I need to do is switch the X and the Y values. So we have negative 3, 0, 3, 5, 8, and 10. Negative 5, negative 1, 0, 2, 5, and 6. Okay, now we can get started. G of H of 6. I need to do the inside first, H of 6. I'm going to look at the original H table. When X was 6, the Y value is 10. So H of 6 is 10. They now want me to find G of 10. And G is the original graph. So I'm going to find where X is 10 and that Y value is at negative 1. So G of H of 6 is negative 1. Let's try B. The inverse of G of H of 0. I need to do the inside first, which is H of 0. Go to the original table for H of X. When X is 0, Y is 3. So H of 0 is 3. And then we need to find the inverse of G of 3. So when I go to the inverse graph of G and I go to X equals 3, I see that the Y value there is at positive 4. So the inverse of G of H of 0 is 4. Okay, let's try the inverse of H of G of 8, starting with G of 8. This is the original graph, so I'm going to go to X equals 8, and that original point is at 0. So G of 8 is 0. I would then proceed to find the inverse of H of 0, which is from the table that we created for the inverse of H. And when X is 0, Y is negative 1. So the inverse of H of 0 is negative 1. So the whole answer is negative 1. Okay. And then lastly, we have the inverse of H composed with the inverse of G of negative 1. So you do the inside first, the inverse of G of negative 1. We're going to go to the graph where X is negative 1. And we're going to go to the pink line because they asked us about the inverse. So when X is negative 1, my Y value was 10. And I wrote the coordinate point there. So G of negative 1 is 10. And then we're going to do the inverse of H of 10. That comes from my table that we made for the inverse, and when X is 10, Y is 6. So this whole thing is equal to 6. All right, you guys, well, that is the end of today's notes. I hope that you guys were able to understand this. If you have any questions, please leave them down in the comments below. Please subscribe, and I will see you in the next video. Bye.